Large language models can be prompted to solve tasks they never saw during training. They can also offer a chain of reasoning, justifying their output. The origins of both these capabilities are still not clear. But we have seen these capabilities emerge only in large models with billion-plus parameters. OpenAI's GPT family models, like ChatGPT, exhibit another less-known capability. They can follow instructions in non-English, even though these models were almost exclusively trained on English. While we don't know how and why the models are able to do this, the tokenization scheme used by GPT is perhaps a necessary requirement for this capability to emerge. Tokenization may not be a sufficient requirement, but it is perhaps a necessary one. This video examines why the tokenization scheme could be a necessary requirement for this capability. Language models use tokenizers to break down input text into individual symbols and tokens. A token could be a full word or a piece of a word. These symbols and tokens are then mapped to unique integers. The integers are indices of learned vectors that are used to represent the model input. The breaking down of input text is driven by a fixed vocabulary of symbols and tokens. The vocabulary serves two purposes. It tells the tokenizer how to break input text into symbols and tokens. It also provides the mapping from the symbols and tokens to unique integers. These unique integers, as mentioned earlier, are indices into a table of vectors. The table of vectors are learned during training. They are learned in tandem with the model training. For instance, GPT family models learn by predicting the next symbol or token, given a sequence of symbols and tokens. The model learns from its prediction errors of the next symbol or token in a sequence. The prediction error quantifies how far off a predicted vector for the next symbol or token in a sentence is from the vector for the actual symbol or token in that position. The error is used to update both the model and the vocabulary vectors. These learned vocabulary vectors are used both on the input and output end of the model. On the input end, they are used to represent sentences, both during training and inference. On the output end, they are used during training to compute error in model prediction. So this raises a couple of questions. How do we choose the vocabulary size? And how do we handle text in any language? Let's start with the first question. The size of the vocabulary is a trade-off. Learning vector representations for all possible words in one language, say English, would make the vocabulary size too large and impractical. On the other extreme, learning vectors, just for each symbol in a language, would make it challenging to learn fine-grained contextual vector representations. Let's understand what a fine-grained contextual vector representation is by comparing vectors from two different vocabularies but trained on the same corpus. Let's say, vector 1 is the learned vector for the symbol A. This learned vector captures all the context the symbol A occurs. Let's assume this vector belongs to a vocabulary of just individual symbols. Vector 2, on the other hand, belongs to another vocabulary made up of both symbols and tokens. Vector 2 captures all the context the symbol A occurs in a token with other symbols, C and S. And vector 3, also from the same vocabulary as vector 2, captures all the context that A occurs with the symbols B and L. Vector 2 and vector 3 are more fine-grained contextual representations than vector 1. They are more fine-grained because they capture two separate contexts that A occurs in specific combinations with other symbols. Those two contexts are indeed present in vector 1 from the first vocabulary. Vectors 2 and 3 are those two contexts separated out. So, we do a trade-off between a rich but impractically large vocabulary, made up of all the words of a language, and a relatively coarse-grained but compact vocabulary, made up of the individual symbols of a language. That trade-off is to learn vectors, not just for the individual symbols, but also fine-grained contextual vectors for commonly occurring words. And more importantly, to also learn vectors for frequently occurring pieces of words, like common word prefixes, stems, and suffixes that can be arranged in a sequence to construct a full word. But how do we handle symbols of, say, Tamil or Russian that occurs in the training text? A multilingual corpus, needless to say, is useful for many tasks. A tokenizer, like the one used for BERT, would map all symbols not occurring in the vocabulary to a special unknown token. But that will map all unknown symbols of all languages to a single vector. This would limit the model's ability to learn about those languages. GPT model tokenizers don't take this unknown token mapping approach. In fact, as we saw in the beginning, GPT3.5 and ChatGPT can follow instructions in non-English, even though these models were almost exclusively trained on English. Does this mean GPT vocabulary has all the 150,000 symbols from all languages? It doesn't. If we examine the vocabulary file, we will not see any Tamil or Chinese symbols. The tokenizer used in GPT family takes a clever approach to avoid having such a large vocabulary representing all 150,000 symbols from all languages. GPT's vocabulary has 256 vectors representing all the 256-bit patterns in a byte. A sequence of one or more of these vectors are used to represent any alphabet in any language. In addition to these 256 vectors, the vocabulary also has vectors for tokens in any language. These tokens are harvested from a training corpus based on their frequency of occurrence. This simple approach enables the tokenizer to handle any individual symbol or token in any language. In summary, any symbol in any language is mapped to a sequence of one or more of the base 256 vectors. Individual vectors are also learned for high-frequency tokens in a language. Low-frequency tokens are represented as a sequence using the learned vectors for symbols and high-frequency tokens. The shared use of 256 vectors to represent any symbol in any language enables the model to learn patterns in sequences across languages. This is not possible with a BERT tokenizer. A BERT tokenizer maps symbols of Tamil language to vectors that are distinct from the vectors English language symbols are mapped to. GPT tokenizer treats all language symbols equally, in contrast to BERT tokenizer. Treating all language symbols equally is perhaps necessary for a GPT model to follow instructions in non-English, even though it was almost exclusively trained on English. However, languages that are overrepresented, both in the corpus used for vocabulary generation and in the corpus for model training, have a distinct advantage over languages that are not. That advantage is due to the disparity in the number of tokens representing a specific language in the vocabulary. In other words, some languages may have more fine-grained contextual vectors in the vocabulary than other languages. In the next video, we will examine the tokenization scheme and the vocabulary in more detail.